The fourth webinar in a series on GCLs. This one is called Practical Lessons Learned from GCL Case Histories. And when I planned this originally, I was going to talk about 3 case histories, and I realized as I was putting this together that would take an inordinate amount of time. So we're going to talk about 2 case histories today, but still cover the key issues that I mentioned when we put this webinar announcement up. We'll have 2 case histories. And if there's an opportunity down in the future, I want to present a 3rd case history on laminated GCLs that we've been using in field applications for mining sites. And we have a plethora of field data now on the performance of those systems. So that may be available in the near future. So if you're interested, keep your eyes on the lookout for that. We have nearly 120 people on board today. I appreciate everybody participating. It's great to have such a large audience. Okay, I'm going to make sure I can press it forward. We're getting started. This is good. Just the past webinar series we've had. I'm going to turn on my laser pointer. I think you should be able to see that. This is the 4th one I mentioned today. And we started last year on the 12th of August. So just over a week from now will be the 1-year anniversaries. But the first one was on fundamentals of GCLs, really the basic principles. Then we talked about bentonite polymer composite GCLs, this new generation of GCLs that are being used extensively in coal combustion products and mining applications, other applications where we have high strength leachates. We had a 3rd webinar on principles and procedures for evaluating chemical compatibility, and a 4th one today on 2 case histories. And a common theme throughout all of these webinars has been the intersection of the geochemical environment and the physical environment. The 2 are both important and really influence the effectiveness of a GCL. And if we really want to understand how to engineer with GCLs and how to deploy them properly, we need to understand that intersection of the physical and chemical world and how it alters the characteristics of the bentonite, 5 being more common, the hydraulic conductivity of the GCL and its ability to be an effective barrier. One note, I will be providing and citing a number of references in the webinar today, talking about those. I've put those on a share file that you have access to. You can see the link at the bottom of this slide. That's a very long URL, and I don't think anybody's going to write it down from the webinar, so I've put it in the chat function. You can go and click on that and perhaps save that link somewhere so you can access it in the future. That folder will contain all the references I cite. It will include a copy of this presentation in PDF. It will include certificates, ultimately, for each one of you that participate, CEU certificates. Many of you need that for your professional engineering licensure. You get 1.5 PDH for today. And then the video from today will be there as well. And this is all free for you to download and use in your practice. The previous recordings for the other GCLs are available as well, as I mentioned. If you're interested in downloading those, I don't expect you to write down these URLs as well, but you can grab this PDF off the share file that I just mentioned on the previous slide and download those if you're interested. They download and just play them right off your laptop. Real easy to use. And feel free, if you want to share these with anybody else, feel free to do so. This is all a public service. And finally, each of you, as I mentioned, will get a certificate of completion. I will get a list of all the participants from Solmax when we're done. You will get an email from me that will tell you where to download your certificate, and they'll be ready in about a week. We have 120 or so people participating, and to be honest, it just takes a while to get all those names typed into the certificates. And But once they're ready, we will get them down, put on a share file and send you out the link so that you'll be able to download those as well. Okay, so let's get into the meat of today's presentation. We're going to really talk about 3 different issues that really tie in with the discussions we've had over the past year in this series. First of all, how are GCLs affected by divalent cation exchange and wet-dry cycling in final covers? We're going to talk about a final cover example in detail and understand why that particular cover system did not function as it was anticipated. And the reason why, as we'll see at the end, is really not thinking about whether the way that GCL was being deployed in that particular application really was congruent with the physical and geochemical environment in which it was being placed. And if we had thought about that beforehand, it would have worked out much differently than the example I'll show. One thing I want to point out, though, before I go any further, is that one of the reasons we talk about case histories is, in most cases, case histories, they're associated with performance that was something we didn't expect, and usually and that's not the case for the vast majority of projects. But the value of looking at examples where things didn't function as we anticipated is we learn about why they didn't and what we need to do to engineer them properly. So I will talk today about 2 case histories where the GCL really was pretty severely damaged by the environment it was placed. And while that's really an anomaly in the broader deployment of these materials in practice, it's important to understand why they didn't function, so that when we engineer in the future, that type of behavior doesn't happen on one of our projects. So getting back into the bullet list here again, 1, how are GCLs affected by divalent cation exchange and wet-dry cycling in final covers? Show an example of that. We'll talk about how to avoid that in the future. And actually very simple things we can do, good practice. How are GCLs in a composite liner affected by exposure of the liner? So we build a liner, GCL on top of a subgrade, geomembrane, but then we stop. We don't build a leachate collection system. We don't put the waste on top. We just leave it exposed. That's a really significant environment when that has a strong impact, can have a strong impact on the GCL. And there's lessons to be learned from that. And then finally, the third thing I'd like to talk about, are laminated GCLs more effective in controlling percolation of final covers than conventional GCLs in covers? And I noticed my last bullet should say than conventional GCLs in covers, and they are. And I will bring that out in the first case history we talk about today. And if we have some time at a later date, I will present another webinar really digging into the 2 very large-scale field experiments, the interior of the GCLs at a mining site in the Western United States. So let's talk about GCLs. I imagine many of you, since you signed up, are very familiar with these materials, but not everybody is. So let's have a little bit more background material to get everybody up to speed. GCLs are prefabricated clay liners, typically 2 non-woven geotextile or a woven and a non-woven, sandwiching a layer of bentonite, somewhere between 4 and 8 kilograms per meter squared, typically somewhere between around 5 being more common. On a dry weight basis, kilograms per meter square. So we have a thin layer of bentonite, half a centimeter thick or so, sandwiched between 2 geotextiles, and those geotextiles are bonded together, commonly by needle punching, where as we produce the GCL, we send it through a needle punching bore, which essentially just drags fibers up and down through the interior of the GCL, binding both geotextiles and the bentonite together. That's the most common technique for binding. Stitching is also used, less common, but effective as well. But in the end, we get a roll of material, essentially a clay liner that comes in a roll, dropped off in a truck at our field site, and we prepare a subgrade and roll it out. We do that very carefully, but it's a very expedient and thoughtful construction process compared to a thick compacted clay layer, which is a very arduous and time-consuming process. What we can do, we can construct a composite lining system, a geomembrane over a GCL, much more quickly and much more effectively and with fewer flaws than we can construct a composite lining system with a geomembrane in a much thicker compacted clay layer. And so there's really some significant advantages in the quality, the expediency, and actually if you look at sustainability metrics, when you begin to look at energy and emissions, there are really great benefits there as well. We look at GCLs and liners. We're typically replacing the clay component in a composite liner like I show here. This is a conventional lining system composite liner for RCRA subtitle D landfill, or for a coal combustion products landfill. We've got a compacted clay layer on the bottom, typically at least 2 feet thick, having a hydraulic conductivity of 10 to the minus 7 centimeters per second or lower covered with a 60 mil geomembrane, typically high density polyethylene, commonly textured these days, so 1.5 millimeter thick geomembrane. That system being replaced by a much thinner barrier over here on the right with our alternative design with a GCL, where we've got a geosynthetic clay liner that has a hydraulic conductivity almost 2 orders of magnitude lower at about 10 to the minus 9 centimeters per second, or 100 times lower than the clay liner. We've got the same geomembrane on top of it, so we've got a much thinner system, and it's a thinner system, and because that GCL has lower hydraulic conductivity, it tends to have lower leakage rates from the thicker compacted clay system on the left. So it's rapid and cost effective, and savings in airspace as well. This is particularly advantageous in clay poor areas. Now the system in a liner is exposed to something very different than what we'll talk about in the next slide, where we're using a GCL and a cover. In a liner, first of all, we may be exposing the GCL to very aggressive liquids. So for example, if we're dealing with some coal combustion products, we can have very aggressive leachate, very aggressive. If we're dealing with mining solutions, we may have very aggressive liners. We're typically in a cover much less aggressive. Secondly, in a liner, and beneficially, it's buried. It's at depth, and significant overburden stress will be on top of that liner. I always say that overburden stress is the great equalizer. We can eliminate all kinds of flaws and defects with high stresses, and that's true in lining systems. As we build up the waste above it, we will consolidate the lining system in the GCL. The pores will get smaller, and its performance will improve over time, getting better and better and better. So it has stress to improve it, and also just the coverage of waste really provides physical and thermal isolation from the external environment. So a lining system may have one more aggressive leachate, but it has benefits in terms of higher stress and protection from other factors. So let's talk about GCLs and covers. Let's talk about the flip side. Again, we look at a typical subtitle D landfill or coal ash type of cover system, where we've got a geomembrane over a compacted clay layer, tending to be a little more permeable for the clay layer than we would have in the lining system. Typically, we'll have a drainage layer here as well. I don't show that in the final cover on the left, but we'd almost always have a drainage layer on top of the geomembrane to promote the slope stability more than anything else. And we can replace that system with what we have on the right, where we have a GCL and a geomembrane on top of it. And on the right, actually, I show the drainage layer, a geocomposite drainage layer shown directly on top of the geomembrane. So much thinner system on the right, and a system that is equally, if not more effective than the one on the left, provided we design it and construct it properly. Getting back to what we just talked about in the liner slide on the previous slide, Here, we're not going to be exposed to really aggressive liquids. We're largely going to be contacting whatever moisture is in the subgrade directly below the GCL. So we'll have some subgrade in which we build it. We may have ions move upward, diffuse upward into the GCL, and we know that happens from the subgrade. But those the pore water in a subgrade it tends to be very dilute, nothing like a very aggressive leachate. And we'll also have water coming down from above. Our primary reason for having the barrier is to prevent infiltration, ultimately becoming percolation into the waste. But that water too will be very dilute. It will pick up salts as it migrates down through the overlying soil layers, but it will not have near the concentration that we would have in a lining system. So not nearly a severe geochemical environment, but the physical environment is more aggressive. It's at low stress. You know, we have a meter of soil maybe on top of the barrier, on top of the geomembrane and the GCL. So the stress is quite a bit lower, much lower than it would be in a liner. And it's got the atmosphere right above it. And the atmosphere in this time of year, we've got lots of root water uptake. It's causing wetting and drying occurring on a regular basis in many parts of the country in August. We really go into water stress in the vegetative zone, and we're drying out these systems significantly. If we're in northern climates, particularly if we get very cold weather before snow comes, we'll have freezing and thawing as well. So, and we don't experience either of those to any significant degree in a lining system, but they do occur in covers. So the physical environment and the chemical environment are both important, and they are different in a cover than in a liner. So those principles are important. We'll come back to those as we kind of talk through this. Let's talk about the chemical environment a little bit more. And if you've been on some of these other webinars, you've seen some of these slides, and I always present them because from my perspective, this is the most important information to understand to be able to engineer with GCLs properly. How we take a GCL, which is two geosynthetic materials containing a particulate bentonite in between that's bonded together with needle punching or stitching, but it's a granular material. And that's what I show here in the upper right-hand corner in this figure. And now this is an artist's rendition, but whether I had a granular bentonite or a powder bentonite or some well-graded bentonite particulate in my GCL, it is a particulate, usually sand to silt-sized particles. And unless that material transforms itself, it will have a hydraulic conductivity like a sand or a silt and not like a clay. And of course, for the GCL to be effective, it has to have a hydraulic conductivity that's typical of a clay, and that means very small pore sizes and much smaller than the artist's rendition would suggest, 2 orders of magnitude lower at the upper right-hand corner. So this material has to transform itself, and it transforms itself when it hydrates, and the transformation that occurs depends on the geochemistry of the water present when the bentonite hydrates. So if we're very effective and we have a water that hydrates the bentonite, those bentonite particles swell, form a gel, we'll end up with a extremely impervious GCL like the one I show here in the bottom. And this is one actually I exhumed out of a lining system or a cover system, a barrier and a cover system in the Sonoran Desert of California, one of the hottest and driest places in the United States. And even in that kind of environment, we can have a GCL swell to form essentially a nearly impervious barrier with a hydraulic conductivity on the order of 10 to the minus 9 centimeters per second or 10 to the minus 11 meters per second. Extremely impervious, where all the pores are at really the nanoscale, where water molecules are making their way through the pore spaces rather than large pores like we might see in the sand. On the other hand, if we're in a geochemical environment where those particles in the artist's rendition above don't swell and don't hydrate and don't form a gel, and there are conditions that happens, then effectively we'll have something that's sand-like, and it'll be very, very permeable, 10 to the minus 5 centimeters per second, sometimes even higher. So this transformation is critically important, and we need to understand why it occurs and when it occurs. So if we think about that schematic that I showed, or the schematic and photograph that I showed on the previous diagram, and zoomed in on the particles, essentially this is what's happening. On the left, this is where we have low hydraulic conductivity. The granules swell, they're imbibing water, they're swelling, and they're closing the intergranular pores between them. And all that's left is a very fine, highly irregular pathway for water to flow. That's what I show here, this extremely tortuous pathway. Very small area for flow, extremely low hydraulic conductivity. On the right is the example where the bentonite granules swell not at all or only modestly, and the intergranular pores don't close. And of course, we end up with a much larger pathway, or a pipe, through which water flows, and the hydraulic conductivity is much higher. What's important is when this transformation occurs, those granules are expanding because they are affiliating with water molecules. Water molecules are affiliating with the montmorillonite mineral surface on the bentonite. And they're not only affiliating, they're electrically binding to that surface. So the water molecules that are swelling in the granule aren't like free water like we get out of our tap. They're an immobile water that's strongly bound to that mineral surface, and for all practical purposes, they don't move at all. There's what we call immobile water in academic speak, and only the very small fraction of mobile water, which may be just 1% of the pore space, is controlling the flow. So why does this happen in bentonite, and why doesn't it happen with all clay minerals? Why can't we build a GCL out of any type of clay? Well, it's because bentonite is predominantly montmorillonite clay mineral, and montmorillonite is a very special clay mineral. And I show here on the right, there's a powdered bentonite on the right, which is predominantly montmorillonite. Montmorillonite is a 2-to-1 mineral, and it's got a series of 2-to-1 sheets, or if in the clay literature called lamella, which are made up of a silica tetrahedral sheet on either side, encompassing a gibbsite octahedral sheet on the interior. And the three are strongly bound together, and they form stacks, one sheet here and then another sheet, or a lamella, as they're called, stacks of lamella. But what differentiates montmorillonite from other clays is that these lamella are not strongly bonded. And many clay minerals, the individual building block sheets, whether they're 2-to-1 or 1-to-1, are strongly bonded by different types of chemical bonds. And so they're very rigidly connected together. That's not true with montmorillonite. There's a very weak bond between these sheets, a bond right here. And these surfaces, which are weakly bonded together, have enormous surface area, on the order of a football field per gram, enormous area. And they're negatively charged, and so they tend to be highly reactive. And so when we put this material in water, these weak bonds allow the sheets to separate, and water molecules make their way into this space, this so-called interlayer region. And that's what causes swell. And we have a highly charged surface, a weak bonding, and water molecules zoom into that space. They push the sheets apart, and that's what we see in bentonite is swelling. And the water that gets into this interlayer region gets actually very strongly tied up with the mineral surfaces and is not particularly mobile. It's so-called immobile water. And in the literature, this is called a D001 space, and the spacing between the sheets, and that expands as there's more swelling. But that's kind of academic nuance of D001. Just think of that. We may be exposing the swell. We're going to use that quantity here in the next slide briefly. But just a couple of points about this that I've mentioned. We get interlayer separation. When that separates, we have very high surface area because that surface is open, it's charged, and it's highly reactive, and water molecules affiliated with it, they zoom in there and cause the system to swell. Well, back in the 1950s, it's even hard to imagine. It's before I was born. I have a lot of gray hair. A professor named Norris did a lot of study on the swelling of bentonite in Montmorillon long before there were GCLs or long before we even had engineered landfills. But he was looking at the swelling of bentonite largely for other chemical and agricultural applications. And what he did is studied how the swelling changed with the chemistry. And he showed two different important things. One, that as you, and he made this graph of D001 spacing from my previous slide, and that essentially could just be swelling. So going from low swell down at 0 to high swell at 14. And he graphed it on the x-axis 1 over the square root of the concentration. And that's a weird set of units to use, but was convenient because it tended to normalize all his data into a nice straight line for making interpretive remarks. And there are also good equilibrium chemistry regions for using that as well. But you can think of the y-axis as just being swell, and you can think of the x-axis as going from concentrated on the left to dilute on the right. All right, so concentrated on the left, dilute on the right. So as we go to the upper right-hand corner of this graph, we're talking about very dilute solutions with a lot of swelling. On the other hand, the lower left-hand corner is very little swelling and very concentrated solutions. And what he observed, and you can see his data here, that as we increase the concentration, as we increase the concentration, we cause diminishment of the swelling. And you can see with this very high swell up here, very low swell over here. He also found that the swelling occurred in two stages. There were so-called crystalline swelling, which is this early part, which occurs regardless of the concentration or the type of cations, and then so-called osmotic swelling that occurred after crystalline swelling. And that crystalline swelling always was essentially the same amount of swell, but the osmotic swelling component was the component that was really affected by the chemistry. And as you can see here in his graph, that as we got more less concentrated or more dilute, there was more swelling. So we know, if you remember in class years ago, when you took some dry bentonite and you put it in a vessel with deionized water, it would swell like 10 times its volume. Deionized water is highly dilute. On the other hand, if we took that same bentonite and put it in a concentrated solution of concentrated salt solution, we get very little osmotic swelling and very little overall swelling for the bentonite. So the one thing was the concentration effect. The other thing that he showed is that the swelling was very sensitive to the valence of the cations. When it was a monovalent cation, a sodium or a potassium, we could get very high swell in dilute solutions. On the other hand, if it was predominantly calcium or magnesium, a divalent cation, or even a polyvalent cation, like some aluminum oxides or other types of trivalent ions, we would only get crystalline swelling, and that osmotic swelling, that's that greasy feel for bentonite, didn't even occur. And I'll show you some photographs that illustrate that really nicely. So a couple of things though, concentration matters and valence state matters, and we'll see that as we go through. I've shown these slides a lot because I think they're just really illustrative. One thing I just wanted to point out as I take a note here, there is a question box. I will take questions at the end. If you have questions, just enter them in the question box, and we're going to go through all of them at the end. All right, I see one from, it looks like Faniva Rarson's got a question out. Faniva, you'll be the first up as we get into questions a little later. Okay, so just an example here, two different photographs shown in this slide. In each case, we ran the old GRI GCL-1 swell test, which is where we took a thin layer of bentonite equal to what would be in a GCL, put it in a Proctor mold, put a plate on top of it, and then poured water on top, and we would measure the movement of the plate or the swelling of the plate. That's how that test was run. And when we were done, we would report that swell as the swelling of the bentonite. Today we use D5890, a much simpler and easier swell test. But these experiments with GCL1 really illustrate the principles I talked about before. So imagine in this Proctor mold, we've taken the dry bentonite, we've put it in the Proctor mold. It's about a 1/2 centimeter thick, just like it would be in a GCL. And then we pour deionized water on top. Look what happens. We go from something that's a 1/2 centimeter thick, which would be about down here on this scale, and it goes up to 4 centimeters thick, or about 40 millimeters. We end up with a gel. It looks like almost like Vaseline or something. It's no visible pores, no evident pore space, kinds of flaws and defects material. That's with deionized water. And it's sodium because the bentonite is delivered in the GCL, and when it comes out of the ground, it is affiliated largely with sodium on its surface. So it's a very dilute solution, the deionized water, and the cation is monovalent. We do that same exact experiment, identical, and we replace the deionized water with a 50 millimolar calcium chloride solution. So we pour that calcium chloride solution on the GCL, and we watch what happens. Everything else is identical. The lower photograph illustrates that. Nothing happens. Virtually no swell of the bentonite. If you look closely, you can see the original bentonite granules in that patty down below, and it's about a 1/2 centimeter thick, the same thickness it was in the Proctor mold before the water was poured in. Virtually no swelling at all. And that's because it's in a divalent solution with a calcium, and the concentration has gone up. So we're only getting crystalline swelling in the lower one, very little swelling at all. And the upper one, we're seeing crystalline, but most importantly, that very bold and significant osmotic swelling. And it's that osmotic swelling that gives hydrated bentonite that greasy feel, in which we rely on in environmental applications, whether it's a liner or we're sealing a water well or building a soil bentonite cutoff wall. In all those applications, we're depending on osmotic swell. Here's another couple of photographs that illustrate these principles. In the upper left, that's the sodium bentonite, same type of material I showed in the previous slide. We're just looking at a close-up. You can see all the bentonite granules have swollen. There's no visible pores. Look at the slide below that. This is calcium bentonite, where the sodium has been replaced by calcium, and we've inundated it in water. No swelling at all. It looks like sand particles. That you would never think of that as a clay particle, but that is bentonite, but it's not swelling. It only has a very modest affiliation of water with the mineral surface, and that calcium bentonite is going to be orders of magnitude more permeable than the sodium bentonite above it. Now, why do we talk about this? Because these chemical issues are what drive the behavior of GCLs. And if we understand them and we engineer with them, we'll be successful. And if we don't, well, we're betting at that point whether we're going to be successful or not. We often use the swell index test as a measure today of that swelling of bentonite. ASTM D5890, really nice, simple test, somewhat cumbersome to do. We developed some simplified methods for this that we use. But essentially, we're taking 2 grams of dry bentonite. That's what I'm showing here on the left. All right, and what we do is we take our liquid of interest, deionized water, leachate, we sprinkle that 2 grams into it very slowly, allowing it to settle into the solution and hydrate and form a gel, which we see on the right. So on the left is the dry bentonite. On the right is that same dry bentonite where it's been deposited in a 100 milliliter solution or a graduated cylinder. And depending on the geochemical environment, we'll get different amounts of swell. Now this one here is kind of right on the margins of whether that bentonite's going to be successful. It has swelled a lot compared to dry bentonite, but the swelling is only about 18 milliliters per 2 grams. Not a lot of swelling. Whereas if we were in deionized water with a good quality bentonite, we'd be up around 30. And in some cases, if we were with a true calcium bentonite, like I showed, we'd be down around 6 or 8, or a very strong solution. So we're somewhere in between the extremes of a a very dilute solution with a high quality bentonite at 30, and down here at the bottom, which we would get with extreme case with essentially no swelling and a calcium bentonite. We'll see there's a threshold right around 15 where things really change, 15 milliliters per 2 grams. As you can imagine, the hydraulic conductivity of the GCL is very much correlated to that swell that we measured in that swell index test. And this is data I've shown before, and I just want to present it again. As the swelling goes up, the hydraulic conductivity goes down. And we get past, there is a transition, or essentially a bend in this curve where the hydraulic conductivity ceases changing substantially, and it is right around here in 15 to 20, which we were just talking about, right? So rapid change as the swelling goes up, the conductivity is dropping, and then it tends to slow down and kind of come to an equilibrium right around 10 to the minus 9. So we look at this. This is, I should point out, these relationships are unique to a given bentonite and bentonite grind that would be used in a GCL. So there's not a universal curve like this. All right, let's take these basic principles and let's spend the next 30 minutes or so talking about 2 different case histories. First one is an older case history, but it's rich with information, and it's a really one of the early GCL deployments in final covers. And this was a final cover in Southwest Wisconsin, which had relied on compacted clay barriers for years for both liners and covers. And when GCLs were brought into the marketplace, there was some reluctance from the regulatory agencies to accept a GCL as an alternative to a compacted clay layer in a liner or in a cover. And this was a coal combustion products landfill, Southwest Wisconsin, at a power plant, was being closed, and the engineer had suggested using a GCL in place of a compacted clay layer. And the regulator, rightly so, was not used to using GCLs much at the time and was somewhat skeptical and said, well, we can do that, but you have to prove to me that it's going to work as well as you say it is, right? And the way we went about proving it, the way they asked them to prove it, is to build a big pan underneath. This was called a lysimeter, essentially a big bathtub right underneath the GCL where you collect all the flow and you transport it off to a collection point, or in this case, a still well, but there's lots of different ways to do that. In fact, lysimeters for covers have come a long, long way since this first case history in Wisconsin. This was actually about 20 years ago now, so it's an older case history, but it's really rich in information. Now, engineers built this and started monitoring it. It had a lot of confidence in the outcome, and thinking about if it's a GCL and the hydraulic conductivity is around 2 or 3 times 10 to the minus 9 centimeters per second under unit hydraulic gradient conditions, just vertical gravity flow continuous, it should be at most about 3 millimeters per year of percolation. And so they began to look at the data and judge whether it was functioning congruent with what the expectations were. Now, before I go into some of the outcomes, I'm going to talk about this in about 15 minutes. You could spend days studying this. There are 2 papers that talk about this issue in particular in the file share that I mentioned. They're just shown here briefly. You'll find them at your leisure. So here, this is the data that they started collecting. And again, expecting about 3 millimeters per year. There were 2 lysimeters constructed, named lysimeter 1 and lysimeter 2. And they were collecting data, and one of those lysimeters started off really low, seeming pretty good. And then the other one, lysimeter 1, not so good. You know, not quite a year out, and you've got 120 millimeters of percolation, and you're thinking it should be about 3 or less. Uh-oh, not so good, right? Something's wrong. So people were thinking, you know, maybe we goofed up when we built the lysimeter, because one of them seems to be working reasonably well. Lysimeter 2 does. Maybe we just made a blunder, went back and rebuilt it. All right, so right at this point, and then started monitoring again. It looks good. Okay, maybe we just made an error, and because now the percolation rate's lower and it's getting about a year old, and same thing's happening again. In fact, it just climbing, and climbing. Very high percolation rates. And shortly after that, delayed for reasons that still aren't quite clear, the other lysimeter too started to climb, and almost at the same rate, just at a very rapid rate of percolation. This is cumulative percolation, so we're adding it up over time, and it was not functioning well either. Now, at this point with lysimeter 1, again, the blue data, when it began to fail again, they recognized, it's unlikely that we made the same blunder twice. And we're also seeing high percolation rates in lysimeter 2. It wasn't a construction blunder. It's probably something about this material. And they looked at another type of material at the time, as a laminated GCL. Laminated GCLs are pretty common in the industry today. This is where we take a geomembrane and we bind it to the surface of the GCL. It may be a little lighter weight geomembrane of 20 or 30, preferably 40 mil if we can do it. Textured geomembrane binded to the top of the GCL, and essentially creating a composite barrier installed just like a conventional GCL, rolling it out, overlapping it, putting bentonite in the seams, not welding it. You can install a cap strip, but that was not done in this case. So they reconstructed lysimeter 1 with a laminated GCL. Very different outcomes, very different outcomes. Very low percolation rates. And so lysimeter 1 is looking great with this reconstruction with laminated GCL, and lysimeter 2 is still being monitored. It doesn't seem to be getting any better. It's just really high percolation rate. So it got reconstructed around year 6 with a laminated GCL, and both have functioned extremely well since. Now, there's about 5-6 years of data with the laminated GCL. I haven't gone back to see if any more data have been collected, but I should point out that I have constructed 2 large test facilities with laminated GCLs and covers in Idaho in a very aggressive environment, hydrologic environment. And the performance of those systems, one of which has been monitored for 8 years, is very similar to what we see here, extremely low. So what happened here? What happened to the GCL, the conventional GCL in lysimeters 1 and lysimeter 2? And what are the lessons we can learn from that? Well, if we look at the data, again, with the conventional GCL, we're getting about 299 millimeters per year, as much as. That's a lot higher than 3, right? That's probably 100 times higher than expected. After it was reconstructed, up to 450 millimeters a year, so even higher, right? So clearly something's very amiss with the conventional GCL. And then replacement with a laminated product, a laminated GCL or a GCLL as they're called, percolation rates have been on the order of 2.6 to 4.1 millimeters per year over a 5-year period. That's very analogous to what I've monitored in Idaho, which tend to be between about 1.8 and 4 millimeters. So very similar. Well, what happened? Well, we dug into the system and looked at the GCL, and wow, what's going on? This is not an image like that nice swollen GCL I showed earlier. This is the bentonite in the GCL where it's been pulled apart. We see dry bentonite, we see cracks, we see some vegetation in the background. Clearly a dried, cracked system. We also saw roots on the underside of the GCL, so the vegetation had come down through the GCL and propagated underneath on the bottom of the GCL. That's actually where we would expect roots to propagate, not within the GCL, but below it, because right at that interface of the GCL and that lysimeter is where the water is going to accumulate due to a capillary barrier effect. But we had roots going through, we had dry GCL, we had cracks. This not what was expected at all. Why is this happening? And also, why are those cracks not sealing back up when it wets back up? If water touches it, shouldn't it swell back up and heal like we saw with a new GCL where the bentonite would swell the large pores shut over time? What's going on here? Well, we look at the exhumed properties and they are striking. The water contents, and I have lysimeter 1 in blue, lysimeter 2 in red, as we showed before. The water contents are a lot lower than what we'd expect for a buried GCL, where the water contents may be well in excess of 100% gravimetric. This system is drying out. These samples were collected at the end of the summer season. That's when there's been water stress in the soil above, so the roots are pulling out all the water that they can out of the overlying cover soils and from the GCL itself and anything below it. They're drying that system out. And as a result, the water contents are low. And in fact, in 2002, when an exhumation was conducted, water content on the order of 20 to 30%. That's really dry bentonite. We look at those bentonites in the Swell index, and we see that the Swell index is really low too, right? Lysimeter 1, somewhere between about 8 and 15. So 15 is that threshold we talked about. 8 is like a calcium bentonite, right? So wow, low Swell indices. We see here for lysimeter 2, it's even lower. It's like a calcium bentonite. I talked about a calcium bentonite being about 6 to 8. Well, that's what it looks like here, right? It's not the new sodium bentonite that was installed where the Swell index would be way up here. For this particular product, it was 24 milliliters per 2 grams. Same thing in 2002, same type of observations. Very low Swell indices relative to a new GCL. And importantly, the hydraulic conductivity of the GCL after it was exhumed, nothing like our new GCL down here at about 3 times 10 to the minus 9. Some samples in lysimeter 1 in the first exhumation were about 10 times higher than expected. But by 2002, they're all very permeable, right? Very permeable, up in the 10 to the minus 5 centimeter per second range. So nowhere near to the minus 9. Orders of magnitude. Wow, what's going on there? Well, one of the things we looked at is, let's look at the surfaces of that bentonite. What's going on? You know, did it change? Did it change chemically? We talked about it's the intersection of the chemical and the physical world and how those two interact that govern the behavior of the GCL. And here in this particular example, I show what are called the bound cation concentrations. These are the cations that are affiliated with the surface of the montmorillonite. And when we get a new GCL, it will be predominantly sodium on the surface, right? That monovalent cation that promotes a lot of swell when it's hydrated. And I show the new GCL is the gray hashed bar here. And then the GCLs that were exhumed from lysimeter 1 are shown with kind of the reddish, brownish colors, the hotter colors, and lysimeter 2, the bluish greenish colors or the cooler colors shown here. These are exhumed GCLs. New, I have about 55 centimoles per kilogram of sodium affiliated with the bentonite surface. Exhumed, where'd all the sodium go? It's gone, right? I have less than 2, right? Maybe 2 in one case. Virtually no sodium. There's a little bit of potassium on the bentonite when you buy it, but there's more potassium now. Where'd that potassium come from? What goes in fertilizer, by the way? Anybody fertilize their lawn this summer? PKNN, phosphorus, potassium, nitrogen, right? PKNN, that's where the potassium comes from. So a little bit of potassium there. That's a lot like sodium. So the potassium isn't really detrimental, but look at the calcium, right? Loaded with calcium, right? Virtually no calcium in the initial GCL, shown here the hash line, loaded with calcium and also with magnesium as well. Where did that calcium and magnesium come? And why does it want to have calcium relative to that sodium that helps it swell so much? Why does that happen? Well, the calcium and the magnesium are abundant in cover soils, overlying a GCL. Actually, sodium-rich environments in a geologic system are unusual. They're present in bentonite deposits in Wyoming because they were marine deposits when they were formed. But they're not common in many of our more common superficial soils. They tend to be more calcium and magnesium. So those calcium and magnesium above were making their way down with infiltrating water down through the system and interacting with the GCL. And you think of a GCL, it looks at, would I rather have a calcium or a sodium? And in a simplistic way, it says for a calcium, I can get 2 charges relative to 1 for a sodium. It's like getting $2 for $1. Sure, I'll give you my $1 bill if you give me a $2 bill. And so the bentonite sees that very preferentially, and we call that there's actually a preferential desire for the calcium from a thermodynamic perspective. But it all comes from the overlying soil layers. And actually it can come from below, from the subgrade too, all right? Now we did some study of this to really get at why all this occurred. And we did samples in the testing in the laboratory and conventional flexible wall permeameters using ASTM D6766, like we talked about in the last webinar. And one of the things we looked at, for example, is it just cation exchange alone? Is it just a replacement of the sodium by calcium? Or is it both the replacement of calcium and something else along with it? Is the wetting and drying important too? And so one experiment we did, and you can't do these kind of experiments in most laboratories because this was a PhD student who was working on this, and he was there for about 5 years. We ran a test with one GCL, where with a dilute calcium solution, like we would see in the pore water coming out of that overlying soil layer, and he ran this test with a dilute solution, just percolating through the GCL for 5 years, all right, over 1,500 days. And you can see over time the GCL started off very impermeable, like we'd see with a new GCL, almost for an entire year. But as the calcium interacted with the GCL, it became more permeable over time. And eventually, when it equilibrated with the calcium, it was 10 times more permeable. And then that leveled out, was relatively constant over time. And this is the kind of geochemical alteration we talked about in the previous webinar. Now, after 5 years, and that takes a lot of patience to run a test for 5 years, we took that sample out and had been hydrated, flowing for 5 years in the GCL. So it's completely saturated, fully hydrated. And then we dried it out on the bench and then put it back into the permeameter, just one cycle, right? We dried it to 50% water content. So not bone dried, something analogous to what we saw in the field. And when we see that, we get this point of subgrade. And the hydraulic conductivity jumped orders of magnitude. Why is that happening? So it's both the calcium exchange, but it's not exchange alone. It's got drying that's important too. We increased orders of magnitude. So if we have calcium for sodium exchange and the GCL desiccates, the hydraulic conductivity is going to increase. It can increase dramatically. So we did a series of tests like this. We did them with GCLs where we put them through different wetting cycles, wetting and drying cycles. We would permeate them to equilibrium, hydraulic equilibrium, then take them out of the permeameter, set them on the bench, let them dry to about 50% moisture, put them back in and run the test again, and ran that until either my graduate student told me she was going to graduate, we call that the graduation termination criterion, or we observed vast changes in behavior. So we look at example with DI water alone, we ran tests, that's the green data, 5 wetting and drying cycles, no change in behavior. That's exactly what we should expect. It may shrink and crack when it dries, but it's still a sodium bentonite, and we put it back in the cell and permeate it with more very dilute solution, and it's sodium rich. It's going to swell back up and seal all the cracks, and voila, stay impermeable. But when we use calcium solutions, and we did this a couple of ways where we first permeated with DI water, and in other cases where we permeated with tap water, but we essentially got the same thing. Eventually, after a number of cycles of wetting and drying with calcium solution, the hydraulic conductivity jumped up dramatically. And there's some delays depending on the initial condition, how we permeated in the first step, but increased orders of magnitude and comparable to what we saw in the field, What's happening? Well, calcium exchange for sodium on the bentonite surface is diminishing the capacity of the bentonite to swell. So for example, if I took that experiment with DI water and I permeated it and then I wet it and dried it, I did it with DI water, you see it, every time I re-wet it and rehydrate it, I get the same free swell. And this is an old GCL-1 swell test, not our common one, but essentially measuring the same properties. We get a really good swell on this bentonite when we're wetting and drying it with DI water. It's a dilute solution, it remains sodium rich. Every time we rehydrate it, that bentonite swells like crazy, all the cracks close up, and the hydraulic conductivity is low. We can do it with tap water, which is has some ions in it, and it diminishes the swell some, but the same type of behavior, really. Really no change, right? Because it's still sodium rich, it's a very dilute solution, and that bentonite is still swelling tremendously. Do the same experiment with the calcium solution. Calcium chloride, dilute calcium chloride, completely different. Within several cycles of wetting and drying, complete loss of swell, right? Complete loss of the ability of the bentonite to swell. And if it cracks and it can't swell back up when it hydrates again, it will remain cracked and very permeable. And that's exactly what happened at this field site. Exactly what happened. You saw the cracks early on in the photograph. Those cracks did not swell shut upon rehydration. Now, the one thing we did too is we looked at that effect of rooting, because that was a question as well at the time. You know, were those roots doing something else? Were they exacerbating the conditions? And we ran tests with these columns in the lab. These were a lot of fun to do, where we built the cover profile with a GCL. We had a silty sand below it and a silty sand above it, and the sand above was the same thickness as our cover in the field, 760 millimeters, or about 3/4 a meter. We ran one column. We actually ran several of these replicates, but columns with silty sand, no vegetation, identical columns with vegetation. They were irrigated on a daily basis with the average precipitation record, and they had solar radiation applied by green lighting in a concurrence with the annual cycle near the field site. So we replicated this rooting system as best we could in the laboratory of these experiments. And ultimately, the upshot of this is, while the rooted systems did tend to dry out more, because roots were taking up water from the system to transpire out through the leaves in the plant, the biomass at the surface. They were drier, but in both cases, the GCL was fully exchanged to a calcium over time, and it was drier with the vegetation, but in both cases, it was a lot drier than we would expect for a GCL buried at depth and fully hydrated, which would be over 100%. Here, even without vegetation, 50 to 60%, because it was drying out in the summer months when we had high solar radiation and episodic moisture. And so our laboratory experiments with and without vegetation indicated, while the vegetation exacerbated the drying, there was sufficient drying in both cases and calcium exchange regardless, that the GCLs became very permeable, in the low 10 to the -5 range. So what did we learn here? And how does it tie in? Well, cation exchange of GCLs occurs as cations in the overlying soils migrate downward and contact the GCL. Unless we prevent that exchange is inevitable, right? So unless we prevent it, it is thermodynamically favorable. Nature is going to cause that to occur unless we prevent it. The other thing is, from below, we can get upward diffusion of cations from the subgrade. So we can also get calcium moving up from below. Second thing, so that's a natural process. So unless we prevent it, particularly one from above, we're going to run into problems. The second thing is that the wet-dry cycling causes shrinkage and cracking of the bentonite, right? So if it's drying, it's going to shrink and crack. That's common in soils. Even more predominant in bentonites because of their volume change. And if those cracks don't swell shut on rewetting, then it's going to be more permeable. And if the bentonite's gone through cation exchange, they won't swell shut, and it will be really permeable. So protect the GCL, right? We have to protect it. And the best way to do that is to put a geomembrane on top of that, right? Put a geomembrane on top of the GCL and then cover it with a drainage layer and cover soils to provide some overburden surcharge to keep things in good contact. If we put the geomembrane on top, we'll prevent the salts from intruding at the rate that they would in the natural system, and I will prevent the wetting and drying. And the product that does that in one material is the laminated GCLs. They work really well and they maintain really low percolation rates, as I illustrated in this data set, and as I mentioned in the field site we have in Idaho. So let's take the last 10 minutes or so and talk through case history 2. This is a very different scenario. Now we're, instead of talking about a cover, we're talking about a liner, but we're talking about an exposed composite liner in California. All right. And this is a unique case because this cell was built, and this was built in central Northern California. I guess I would say it's between San Francisco and LA area. I don't know whether you'd still call that Northern or Southern California, but I'm a Midwesterner, you have to forgive me. But it's a moderate Mediterranean environment. It's got a dry summer, a wet winter. The site was composite lined, fairly steep slopes, 2-to-1. It's a Subtitle D landfill, and it was built at a time when there was some economic disruption, and the cell never got filled. The lining system got built, and then it stayed that way. It was never, a leachate collection system was never placed. Waste was never placed on top of it. And 12 years later, a decision had to be made what to do with this system. Did it need to be essentially torn out, which was ultimately what was done, or what was the condition of the geosynthetics, the GCL and the geomembrane? Geomembrane was studied as well. We're just talking about the GCL here today. Is exposed for 12 years. And during this 12 years, you can imagine that black plastic in the environment. You can imagine the solar radiation. Hot during the day, 120, 140 F on the surface of the geomembrane, cool at night as that black body radiates the heat back upward, wetting, and it's cool, heating and cooling each and every day, and that's going to have effects on the system. There's a publication on this as well. That's on the file share that you can download. And at this site, and I want to recognize, and I got a little animation here. Nasli Yesler and Jim Hansen of Cal Poly in California, who this was their field site, and they invited us to participate in their study. They had the insight to do this work, and we participated and did the GCL testing. But there were different transects on the one side of that cell that I just showed that were sampled. A south slope transect, a southeast corner slopes transect, and the east slope, and an anchor trench as well. And you'll see a little later on, I've affiliated these two anchor trench samples, the one sample with the east slope transect and the lower one with the southeast, although recognize that these anchor trench samples are somewhere in between those two. But sampling along the length of the slope, so one at top of slope, mid slope, bottom of slope, and then a couple of samples in the anchor trench. The anchor trench is important because it's the only part in the system where the GCL was actually buried. The geomembrane and the GCL were not buried in any other area. Exhumed samples look like this. I show on the left, you can see cracks in the bentonite. They're sealed in plastic, brought back to the lab, opened up, took samples out of those for hydraulic conductivity testing and for other types of properties. And tested them for swelling, cations in the exchange complex, hydraulic conductivity, and I'll talk about that in a minute, but also looking at the physical attributes of the bentonite. What does it appear to look like? And here are 4 different photographs going downslope, from the top one being in the anchor trench where it's buried, one at the top of slope, right? That's the next one, top of slope, one mid slope, and one bottom of slope. All right. So let's look at the anchor trench. You can see the remnant bentonite granules. It looks like they've gone through some swelling, right? They're not completely dry. There's been some wetting to them, perhaps due to moisture collecting in the anchor trench and migrating down, but it's not like we had a complete gel there that might have desiccated and cracked. But you also see there's a lot of structure here. Apparently swollen granules, but there's pores between them. Maybe they have dried out some, and that's created some more pore space. But something that has wetted, perhaps dried, and has lots of appears to be permeable area between them. Top of slope, you'll look at that cross section. It looks like granular bentonite, like it's brand new, like it never got hydrated, right? And I don't think it ever did. Water content 14%. practically nothing. Whereas in that anchor trench, it's 34%. So it clearly got wet at some point. Mid-slope, wetter, right? It's not a whole lot wetter, it's 25%. And you can see more swelling of the granules, but you should also see cracks between them and intergranular pores. Clearly a material that's got lots of pore space, lots of flow paths. And then at the bottom of the slope varied a lot. We'll see some of this in a bit. Some areas look very gel-like, no apparent structure, relatively high water content. Others had desiccation cracks depending on where we were. So as we move down the slope, we're getting very different conditions. In some cases at the bottom of the slope, when we open up the GCL, there's no bentonite, complete, essentially near total loss of bentonite. And that's the bentonite erosion that Carrie Rowe at Queen's University in Ontario has done an extensive amount of work on. That bentonite erosion process, which I mentioned, is due to that thermal cycling. When we have the sun up here beating down on our high density polyethylene geomembrane, heating it, because we haven't covered the system, that geomembrane actually separates from the GCL, and we get moisture moving upward, filling that void space. And as it cools in the evening, moisture condensing on the lower surface of that geomembrane and just rolling down slope and to the bottom of the toe. And you can imagine that some of this material is drying out. Some of it's probably wetting down near the toe. And you see as that water is trickling down, it's carrying bentonite with it. That's bentonite erosion. And you can see this eroded bentonite right on the surface of some of the GCL samples. These rivulets of bentonite. So we have probably wetting. We probably have wetting and drying. We have erosion, in one case, near complete loss of bentonite. And probably ion exchange as well. Let's look at the mass per area. New GCL, about 5 kilograms per meter squared. Advertised as 4.6, but probably about 5 in the field. So up in the anchor trench, really no loss of bentonite. A little bit of loss at the top of slope, more at the middle of slope, and that's from downslope erosion, right? So example, on the east slope, about half of the bentonite remains mid-slope. Southeast slope, almost around new, and the south slope, almost like it's accumulating. Well, you can imagine if it's migrating down from the top of slope, it may be accumulating mid-slope and downslope. And when we get to the very bottom, we see really variable results at the toe of slope. At the east slope, a lot of accumulation. And there was one area that Nazi and Jim referred to as the bentonite mound or mountain, where it just bentonite had accumulated at the toe, nearly double what would be in a new GCL. Southeast slope, some accumulation, and the south slope, very low bentonite mass per unit area. So like new, in the anchor trench in terms of mass per area, slight loss top of slope, variable mid-slope, and toe of slope variable as well. Let's look at the hydraulic conductivity. Well, we got highly variable conditions. We look at, and a new GCL should be about 3 times 10 to the minus 9 centimeters per second. In the anchor trench, 2 samples, very different results. One sample, almost 10 to the minus 4 centimeters per second. One almost like it was brand new, right? If we had it in the anchor trench and that anchor trench accumulated water and then it went through some wetting and drying over time, you can imagine that bentonite, that GCL is going to become calcic or calcium rich over time. It will shrink and crack, and you saw some of that in the photographs I showed, and become very permeable. On the other hand, it may not dry depending on where that anchor trench is located and remain like a new GCL, so highly variable. Top of slope, almost like new, right? Low hydraulic conductivity like a new GCL, and that, you looked at that photograph, you could see the granules. It looked like that GCL had just been placed. It hadn't been affected at all, had not really hydrated, had not undergone wetting and drying, and really probably no exchange because it never hydrated. Mid-slope, highly variable. One spot where it remained very low conductivity, and 2 very, very permeable, even with significant bentonite remaining within the GCL, and then very permeable at the toe slope. Now, interestingly, at the toe, I said some areas were cracked, others were not. Environment and the chemical. Why is this occurring? Well, let's take a look at the samples. We see that this is swell index on the left. Again, 10 would be low. This is calcium bentonites. 25 would be high for a sodium, like a sodium bentonite. And we can see that the swell index very closely with essentially the fraction of bound cations that are comprised of sodium and potassium. At the top of slope, they're like new, right? The toe of slope completely exchanged, right? Very permeable. And then at the mid slope, well, it depends. Some are like new and some are very exchanged. And the anchor are the same. The anchor is certainly undergoing some transition. We look at the hydraulic conductivity of the samples, very closely tied to the swell index because it should be, right? We know that's the case. Very permeable when the swell index is low, less permeable when the swell index is high. In fact, almost a step function. And if we look at some other factors, again, wet dry cycling, really clearly evident. South slope, toe, desiccation, cracking, clear there. East slope, toe, desiccation, cracking as well, although it still had some swollen nature of that bentonite. You can see the cracks. Southeast toe, here it looks no desiccation cracks, looks like gel, but when we permeated it, we found that the flow was occurring through the needle punching fibers. So even so, it was still retaining some gel type structure. Its ability to swell up and seal the fibers was no longer effective. So what are the lessons learned from this case history? One, well, GCLs and exposed composite liners are seriously affected by downslope bentonite erosion. We saw one GCL, almost all the bentonite was gone, combined with the effects of cation exchange and wet dry cycling. Those impacts are greatest at the toe, apparently due to inability of the bentonite to swell and preventing closure of cracks from wet dry cycling and sealing of the needle punching fibers. And then finally, the geomembrane, this has a geomembrane on top of the GCL. We talked in the previous case history, put a geomembrane on top. Well, that geomembrane can't protect the GCL if there's no overburden on it. It's got to have something that keeps it in contact and keeps it tight, right? And so cover the geomembrane soon after installation with sufficient overburden to ensure an intimate contact. And that's going to be at least the leachate collection system. And ideally, you want to get waste placed fairly soon after you get the collection system in place. So related lessons, but for very different scenarios. Cover, liner, different conditions, physical conditions, different chemical conditions, and yet similar lessons to be learned. General lessons, one, hydraulic conductivity of GCL is controlled by chemical and physical conditions that influence the ability of bentonites to swell and fill the pores that control webinars. You've seen some of these slides, the chemical conditions and the physical conditions to engineer properly with GCLs. Geomembranes used in covers without an overlying geomembrane are prone to damage. I would be very careful about using a GCL alone in a cover without a geomembrane over it. Use a geomembrane over the GCL, creates an extremely effective system. Percolation rates on the order of a couple millimeters per year. Really, really effective. And without it, that GCL loses its effectiveness in many cases in short term. And composite liners, if we don't cover that composite liner with surcharge from a leachate collection system and waste to keep everything in contact, to keep the geomembrane intimately in contact with the GCL, we will damage the GCL over time. We want to make sure we want to get it covered soon, and we want to apply sufficient overburden. And finally, and I just talked about this briefly with laminated GCLs, this issue of covering the GCL and putting overburden on top, we can simplify that using laminated GCLs, products where the geomembrane and the GCL come together. Percolation rates, highly effective in final covers on the order of 1 to 4 millimeters per year. We saw that in the first case history, and I mentioned another field site where we see that as well. So those are the two that we talked about today. We took about 70 minutes to do that. I'm glad I didn't put the third one in, and we'll take some questions now at the end. And as I answer questions, I wanted to put this slide up as well, because it's important to note that, while I'm the one doing the talking today, there are a lot of people that contributed to this, and really the intellectual development here, and the knowledge creation really depends on a lot of contributions from other folks. And so a list of students and postdocs over the years and other faculty I've worked with that's really have influenced a lot of my thinking. Okay, so I got some questions we've got, and if you've got more, just add them in the questions chat. I have a question on the hydration liquid. Does any liquid work, processed water or charged water, for example, or should it be clean water? And that's from Faniva Rarison. And it's an excellent question. As you've seen here in the presentation, the chemistry of the water is particularly important. We want and it's particularly important when the GCL initially hydrates. And so ideally we want it to hydrate in a dilute environment. In the laboratory, we should be using water for testing, which mimics what we're going to be seeing in the laboratory in the field, because the outcomes will be influenced by that significantly. Question from Andy Durham: how does desiccation of montmorillonite compare to that other types of clays? Another really good question. Montmorillonite, because it's geosynthetic materials containing bind water, also has the ability to shrink and swell significantly, because it swells so much because it's binding water, right? And it's that binding of addition of water molecules that's making the clay swell. When we have enough energy available to pull those water molecules back out of the system, and that's really what it is, it's pulling them back out. Like for example, roots penetrating down through systems. Roots have great propensity to pull water out of soil. If there's enough energy to pull that water out, well, it causes the opposite of swelling. It causes shrinking, and that's bentonite, because it swells so much, also shrinks a lot too. So it has the greatest potential for shrinking as well as swelling. Yeah, these are like almost primed questions for me that go to the principles. Thank you, Andy. I appreciate that. Here's one from Daniel Adelke. Could you kindly share the presentation link? Thank you. That's shared in the chat. So you've got it early on, and I will be emailing it out to everybody as well. From James Mosley: what is the minimum overburden to prevent damage to GCL in a cover system, assuming there is a geomembrane covering it? Well, I can't answer that with great specificity, but about 1/2 meter is what you need to keep good contact between the geomembrane and the underlying GCL. If you want greater thermal protection from freezing and thawing, you might want to go somewhat thicker, but we also know that GCLs are very resilient. They can freeze, they can thaw, and they're not damaged in the same way a conventional clay liner is. That's a story for another webinar. But so about 1/2 meter is what I would recommend as a minimum. Preferably 3/4 meter to 1 meter, but 1/2 meter is probably the minimum. Good question, James. That's enough overburden to keep that geomembrane in intimate contact with the GCL. Question from Sean Monks: what are some ways to prevent cation exchange from underlying soils when using GCL in the bottom of composite liners? Really good question, and one I just touched on delicately here today, but insightful thought question, Sean. We do get upward diffusion of ions from below, and we see this, and there's almost a race that goes on in the bentonite between its ability to hydrate and its propensity to undergo exchange. So you have water moving up from below, calcium and magnesium moving up from below, and that bentonite is saying, I'm going to take every one of those calciums I can get and reject these sodiums because I get 2 to 1. But it also sees moisture coming up as well. And it also wants that moisture, and it's almost a race to which happens more quickly. If you prepare your subgrade in a moisture condition, the hydration will win, and it will swell before it exchanges, and you'll retain nearly all the hydraulic conductivity. If you're interested, and I put this on the website, we have a case history at a site, Barnwell, South Carolina, where we exhumed a 10-year-old GCL where it had completely fully exchanged with calcium, but it had undergone full osmotic swelling before it exchanged and still retained very low hydraulic conductivity. So if you want a simple answer, what are the ways that we can minimize the impact of that ion exchange from below? put it on a subgrade that's at least optimum water content, preferably 1% wet of optimum water content. That will help the hydration win the race. Kenneth Bergschultz, doesn't a GCLL create a slope stability issue with the bentonite? It's hydrated and is not reinforced and creating a thin veneer layer. Yeah, good question as well. All these systems have complexities. The laminated GCLs have the products I've dealt with, a geomembrane laminated to an upper non-woven geotextile, and then the non-woven geotextile is the upper part of the GCL. So that's like the same thing we would see if we had a geomembrane and a GCL in a composite liner or in a composite barrier and a cover. But there is propensity for bentonite to migrate up and affect that interface. So the interface shear testing is critical to make sure that the stability of that system is sound, that we retain sufficient interface strength, and that we won't have a stability failure. And any time you're designing a slope, understanding the stability issues are equally important as the hydraulic issues. And that requires appropriate laboratory testing under conditions that mimic what's going to happen in the field. We've got about 7 minutes yet, but if people are willing to stay on, I'm going to keep answering questions until they cut us off. How's that sound? Question from Eric. These are really good questions, by the way. Thank you. Eric Lamontague, I hope I pronounced that properly, Eric. Were the carrier fabrics in the testing woven or non-woven geotextiles? And I have to go back and look. In some cases, they're both non-woven. Some it's a woven and a non-woven. Particular products, particular applications, I can't remember, but they're probably described in the articles. So in these particular case histories, if you look in the articles I put on the file share, which is in the chat, you can get that link, and they're there now, and I will also be sending it out to everybody. Thank you, Andy, for the thank you. I appreciate that. Question from, it looks like Aisha Jacob. How to prevent calcium diffusion from underneath the GCL to prevent crystalline bentonite structure? And this is a very similar question to Sean's earlier. Get the subgrade as moist, optimum or 1% wet of optimum if practical, and that will allow it to hydrate before calcium exchange will become significant. And look for the case history in the file share by Scally et al. 2017. That's our case history from the Barnwell, South Carolina field site, which illustrates that really nicely. From Sonia Samir, can we use a GCL with 1 foot protective cover as the bottom liner, since it will have overburden and not be exposed to wet dry cycles as cover? You can. It's yes, this is a good question. Can I use a GCL alone as long as I put some cover on it in the liner and then place waste on top of it? That's a viable scenario, provided the leakage rate from that GCL alone application is sufficiently low. And that would be a site-specific issue and regulatory-specific issue. But yes, you would, with that protective cover and then building on top of it, you would be able to protect the GCL from my experience. From Spencer Harvey, here's a little longer. I got to open up my chat box a little more. Would you expect calcium exchange on GCL placed directly on a soil rich with cemented calcium carbonate in an arid region, less than 20% of precipitation on average? The GCL is part of a composite liner with active leachate collection system. Yeah, if you put a GCL on top of a calcium rich subgrade, you will get exchange. And if that subgrade is not moist enough, you will probably exchange it with calcium before it fully hydrates in a sodic environment. I've run into this. Actually, we have I'm going to put it on the website and make a note here. A great case history which describes that. The effects of these subgrade water contents and calcic versus sodic subgrades and how they'll affect the GCL. So I'll put that on the website. Just make a note of that. I'll do that when we're done today. It's not on there now, but I will. Thank you, Spencer. Good question. This one got cut off. The name is cut off. Kula, Ramchandran Kula, I can't see the rest of the last name, I apologize. Does a leak detection system, geocomposite, provide some thermal cushion if a double liner GCL, not double composite liner, below the LDS geomembrane? The leak detection system below the GCL does provide some benefit. It creates not only thermal protection, but also and this is in a liner, where we've got a GCL and we've got a geocomposite drain below it as a leak detection system. And that leak detection system will do a couple of things. One, it's a leak detection system, and it will provide some thermal buffering because it will not be saturated, and the gas phase in there will be less thermally transmissive than the other materials. But the other thing that it does is it creates a capillary break, because it's a coarse textured drainage layer over a fine textured GCL, and that will tend to cause water to be retained within the GCL, which is favorable. I'd be interested in your field site and learning more about what you're doing on that, Kula. That sounds very interesting. From Pitya Pantana Anake, I hope I pronounced that properly, Pitya. Should clay compacted layer be wetted before GCL installation to assure another in this drawing in the Yes, if you're placing a compacted clay layer or any fine textured layer and then the GCL on top of it, at least optimum water content, all right? If it's dry of optimum, it's not gonna be wet enough, and you need that moisture in there to hydrate the GCL, and we want that hydration to occur quickly relative to other factors. So yeah, good question. I tend to, again, optimum water content or wetter. Kritin Tarnowski, hope Katrin, I pronounced that properly. Would the inability to swell at the toe be greatest a regular case when the liner is staying exposed? That issue about loss of swell and damage at the toe is most significant if it's exposed, right? If it remains exposed, we're going to have moisture accumulating at the toe. It's going to wet and dry at that toe. We're probably going to have erosion at the toe. We're going to have ion exchange at the toe. And we saw in that previous example, the case history 2, all of the samples at the toe were extremely permeable, right? When it had remained exposed. Now that was a extreme case, exposed for 12 years. If it's exposed for a couple of weeks, that's something else. But if it's exposed a year or two, that's not good practice. We want to get it exposed as practically, as soon as practical. Terry Daigle, that's a familiar sound. And Terry, we've been talking about these issues. For subgrade soils, how deep can ion exchange influence the GCL above? 3 inches, 6 inches, 12 inches. Could an imported subgrade layer be useful? Excellent question. Yes, and you can actually calculate how deep that penetration will go, but it really is not very deep, because we've only got at most a centimeter thick of bentonite to satisfy, right? And so 3 inches, 6 inches would be probably enough. I haven't done that analysis, but a really good question. And Terry, we'll circle back on that with the project we're working on. Maybe that's a solution if we need it to be. Thank you. Really good question, Terry. And good to see you on here today. Thank you, Eric. I appreciate the remark. And then finally, again, from Isla Jacob. Yes, my question was answered. Thanks. Thank you. Thank you. I appreciate it. And then here's Jimmy Youngblood. Jimmy's from Solmax, a good friend of mine and colleague. Could a coated GCL be used to protect from ions underneath the GCL? Certainly can. It's a great example. And I wish I would have thought of this earlier, and I wasn't thinking about it in the previous question. But a coated GCL is the same as a laminated GCL. It's just a different type of laminate, right? And in this case, you're just flipping it upside down and putting the laminate at the bottom as opposed to at the top in the cover. But yeah, that laminate or that coating is going to provide that protection. So yeah, another example of where we could use a innovative product to solve a practical problem for a site-specific issue. Yeah, good question, Jimmy. And I think you manufacture those products, so very pertinent that you brought that in. I appreciate it. Any other questions from the group? We're a couple minutes over. I appreciate everybody's willingness to stay on a little longer. I got one more from Pitcha. We'll answer that and then we better finish. Follow-up question. Could landfill use any water sources to wet the surface? Should a tap water be required to wet the surface before the GCL installation? I think you want to be thoughtful about what water source you use to compact the subgrade. You wouldn't want to use a salt water, for example, but it doesn't have to be deionized water as well. One thing you could do is just look at the water you're using and run a swell test on the bentonite from the GCL. If it's not affected by that water, then it's probably going to be a good hydration water for the subgrade as well. That would be a good way of kind of checking the relevancy of whatever water you're going to use. But there's a lot of waters that you could use in that case, and that would work. And that swell test would be a good, quick way to be able to check it. Take your hydration water for your subgrade, run a swell test in the bentonite on it. If it swells comparable to what you get with tap or deionized water, it's probably fine. Good question. Thank you. Okay, well, I think we'll end here. Again, this has been a lot of fun, really good questions. And that's why we do these things, having the opportunity to, I've been really fortunate in my career to work on all these wonderful projects, learn about all these materials. And one of the things that I want to be able to do, particularly at this latter part of my career, is share as much of this as I can with other people. And I appreciate everybody joining today and participating and asking such thoughtful questions for the group to learn from. I hope all of you find this useful. And look for some other webinars in the future. I think we've got a lot of other things that are interesting to talk about, and I hope you'll join in. So have a great day, and I will send out an email that has all the information and links to get the related materials, the PDF of the presentation, and the certificates in the video. Thank you. Have a great day. Bye-bye.